Sorry, it was too cold over there in the shade. So now I'm standing in the sun again, but I'm gonna get a headache. It's tough, right? What I could do is just do voice over PowerPoint at my desk. But that's boring. It's boring for me to record. It's boring for you to watch. So here we are. We've finished all the bending stresses for the idler and for the pinion and the gear. And now we're gonna take a look at the surface stresses, right? This is now like fully new stuff for the first time this semester. All right, so let's find it here, surface stresses, right? We talked about these a little bit in that previous video, and we discovered that the maximum stress, the maximum pressure, works out to be a function of the radius of the two cylinders, and it has to do with, and it's a function of the elastic properties of this material, right? What elastic properties are we talking about? That's all here. Poisson's ratio. Someone asked a great question about that in lecture the other day, that yeah, the stresses in different directions under a contact, right, are a function of Poisson's ratio, right? If I'm pushing straight down, actually, that was a good enough question. I'm going to talk about that a little bit. So the question, oh, here, let's get Cece here. Hey, Cece, are you going to come out? No, okay. She's being, I told her she's got to be a little bit quiet. Okay, so back to this camera. So if I have two cylinders, right, pushing on each other like this, you'd think it'd all be normal stresses this way. But there are stresses this way and there's stresses this way, axial stresses and radial stresses, tangential stresses, because of Poisson's ratio. So we need to know something about the stiffness of the material, Young's modulus, and we need to know something about the how it behaves, how it deforms under strain, that is Poisson's ratio. So that was a great, I was really pretty happy with that question in class the other day. So anyway, that we're going to call this delta, right? But when we do it with gear teeth, right, we can't really say that the gear teeth aren't cylinders, so they don't really have a radius per se. So we've got to do a bunch of crazy geometry here, some crazy geometry there, some crazy geometry here, to really get, and so B is analogous to L. That's the only simple thing about this whole thing. And we're really only concerned with the tangential force. Actually, we're with the contact angle phi, we incorporate for the fact that the whole force exists. Actually, it's the cosine phi there. So you can see that these are related, right? So we're treating this very much like two cylinders, and the contact stresses between two cylinders. All right. But this would be a disaster. I mean, this is horrible. Horrible. Right, so what we're going to do is we're going to take all this material-related property, and so that really is, I guess it's just this stuff, right, and this, and we're going to put those down into here, right, and we're going to say we've got two different materials, potentially, and then a bunch of different properties, and we'll just have that one CP. Now you could calculate this. We know that Nu's or Poisson ratio for steel is about 0.3. Modulus is about 30 gigapascals, something like that, or 207 gigapascals. It's right in front of me. But we've tabulated that, right? So we know that these are our most common materials for the pinion. These are the most common materials for the gear. And so in our case, we're just going to use steel on steel. So steel on steel. My elastic modulus works out to be, my elastic coefficient works out to be 191, right? And the units here are square root of megapascals, right? It's 191 square root megapascals, all right? What the heck kind of a unit is that? All right, well, the next thing we're going to do, we're going to look at this geometry factor. And so, everything that has to do with like the shape of the gear, this stuff here, this stuff here, this stuff here, I think that goes in there too. We're going to condense that all down into this. And so this R here, this R is actually the diameter ratio. That stands for ratio. It's not the radius of one of the gears. Again, you can't just look at an R and say, oh, radius, right? You have to say, what is this? Read the fine print. So we do all this. What's on my next slide? All right. So if we calculate this for our particular problem, the issue here is that we have two different R's going on, right? And consequently, two different I's, two different geometry factors. So the I well, I'll do the R first. R for the pinion to idler, interface is going to be 1.2, leading to a geometry factor for the pinion idler interface of 0.088. 0.088, right? And that's all dimensionless. And then the R for the idler gear interface is going to be 2.88. And that leads to an I for the idler gear interface of a 0.119. Right. So now, right, earlier on, I'm getting bored here looking at the numbers. Earlier on, remember we said, well, oh shoot, what's the tangential force? And the tangential force is the same everywhere along, right, to keep everything in torsion equilibrium. Oh, what's the velocity? Velocity is the same everywhere to keep things from slipping, right? Gears don't slip and they're in torsional equilibrium. So that's easy. But now, finally, due to these geometry effects, we've actually got to deal with the fact that they're different sizes. Okay, so now we've got to trace these two things. And then we can see that this part here is square root of a stress, megapascals. Our elastic coefficient is square root of megapascals. And so we're going to wind up, we can boil all this down, use the same factors we used before, and get these the Hertzian stresses, the contact stresses within the gears themselves, right? And this is going to be a repeated loading. So now we're going to have what's called surface fatigue. The problem is we now have two different stresses, right? And so sigma for the PI, so that's the pinion idler interface, is 1221 megapascals. And then for the other one, 1049. And that's for the sigma for the idler to the gear. All right. Okay, so finally we have two different stresses. Well, we got to pick the higher one, right? Why is that? Because I'm going to draw the top view of this. Let's say I've got this cylindrical-ish pinion, and then I've got a cylindrical-ish idler, and a cylindrical-ish gear, right? It doesn't make any sense to make one of them shorter than the other, right? So, my opinion has to be the same width as the idler. Otherwise, they're going to have drastically different stresses because it's the same force, the same gear tooth. So drastically different stresses. That's no good. So they all have to be the same width, but due to the contact, due to the different radii of the gears, I'm going to have different surface stresses. So what I have to do is pick the higher one, right? 1221 versus 1049. 1221 is the worst one. So this is going to be my contact stress. Now, and that's also for the smaller one, right? Is that indicated back here anywhere? Yeah, because it's based on the diameter of the pinion here, right? And the pinion is typically the smaller one, so that's the smaller one. Because just based on the reason that we use the smaller one is because that tooth, based on the shape of it, will have a smaller radius, which leads to a higher stress, right? So this is going to have the highest stress. So oftentimes what we'll do is just make the pinion harder, right? But anyway, what are we talking about? Okay, so we've got roughly 1221 megapascals. Wow, that's up there. So let's, what do we got here? Surface fatigue strengths, right? The reason I put this in quotes is because unlike, fatigue and bending, it will fail. This will fail. So we have to define this. It's not like we can go an infinite number of cycles. It's 10 to the 7th cycles, right? And instead of 50% reliability standard, it's 99% reliability. So we've got some stuff built in already to this. But this is the fatigue strength that will last at 99% reliability, 10 to the 7th, 10 million cycles. All right, so what do we got? Okay, I don't care about KSI. 69 megapascals. Oh, this sucks. Hold on here. Hold on. 69, and I've got 1200. So I just spent like an hour and 10 minutes working on this stupid problem to find out that my contact stresses is 1200 megapascals and it's only good for 69 megapascals. That's a factor of like 20 off. This is horrible, right? Yeah, it is horrible. That's why we don't make gears out of steel, right? Carbon steel isn't even in the ballpark, right? It isn't used. So we use flame hardening or carburizing or case hardening or nitriding, right? It turns out that using these techniques and changing the actual crystalline structure of the metal just on the surface. We still want something nice and soft and bendy in the middle, but on the surface we want it really hard. So we can get it up to 1200, 1300, right? And so what did I have? Oh, look at that. Look at that. I can case harden it to 1200 to 1300, and I'm at 1221. Awesome, because that gives me, could I do this in green? I can't find green. That gives me an N of 1.024. Just perfect, all right? That worked out well, because I do these in ease. And I can tweak everything until things work out. That's the advantage of doing stuff in ease, not a calculator and paper. Okay, so that's that. Now, the fact of the matter is that this is for 10 million cycles. What if I needed to last more than 10 million cycles? I was just chatting with my mother-in-law, right? I was chatting with my mother-in-law recently because she thinks it's funny that I spend this much time working on gear hardnesses and gears. She drives a Honda. I'm gonna go back here. Right, so my mother-in-law drives a Honda. This is a car, right, that's going to go 250,000 miles, right? So how important is it? That pinion is just hard enough to survive, right? Make it too hard and it starts to crack and fatigue and bending, right? Make it too not hard enough and then it's going to fail on surface fatigue, right? Same deals with all the pinions and the idlers and the gears and all these parts have to be just perfect in order for them to last 250,000 miles. That's way past 10 to the 7th cycles, way more than 10 million cycles. So how do we deal with that? So we've got some surface fatigue strength modifying factors, right? So we said that this is based on 10 to the 7th, right? Well, if I want to go more than that, if I want to go 1 billion cycles, right? Or if I want to go 100 billion cycles, which might be the Honda, then I got to go way over here, and that drastically reduces my fatigue strength, my surface fatigue strength, right? So that does that. Likewise, if I want higher reliability, right, that also reduces my surface fatigue strength. So it's amazing that these cars or these parts are artificial hips. Just don't last that long, right? So it's that's it. And that was long. That was a lot of videos. It's going to take me like 6 hours to upload all these to YouTube. That's what it is. But hopefully then you based on these videos, this example problem, and your book, you'll be able to take a good crack at your project. Okay, thanks for watching.